I'm glad to give a talk about the dry friction, and you will see the dry friction from this talk from a new perspective, completely different what is known in mechanics, because I will focus on the optimization algorithms, how to use dry friction to design efficient algorithms for minimizing functions, okay? And as you see from this title, I will use the iPad. See, this is why I'm not looking at the camera exactly. From the title, there are several keywords. And the first one is, of course, proximal inertial algorithms, okay? Dry friction and Hessian-driven damping, okay? Do you see when I'm writing?
Yes.
All right, good. I am highlighting some few keywords. This is joint talk with the Professor Idi Atouche from the University of Montpellier, and I see that Idi is online. So hi, Idi. If you have also a question, you can answer. And for this, concerning this workshop, I am in the area of set-valued analysis and friction. And of course, today I will not talk about the plasticity, okay? So let's switch to the first second slide. And the beginning of the story is a paper that we wrote with Idi Atouche and Alexandre Cabot, finite-time stabilization of nonlinear oscillator subject to dry friction. It was appeared in a special issue dedicated to Jean-Jacques Moreau for his 18th birthday. And the context is the following. I have to go back to this context. We have a second order dynamical system that you see here that we call the heavy ball with dry friction. You see here, this term is the acceleration. This is the viscous damping. And here we have the dry friction that I will call, and this is the potential, okay? T is as usual, the variable for the time. And this model here that we have for the set valued map that I have here, it models dry friction, called also this Coulomb dry friction in mechanics. And I will suppose some assumptions about this function. And my function phi here, which in the whole talk gonna be dry friction, is supposed to be convex, continuous, because H here is Hilbert space, could be infinite dimensional spaces, with a sharp minimum, as you see here, the minimum of phi is 0, okay? And 0 is in the interior of the subdifferential of phi at 0. Typically, this is a function like R times, I have to draw here some function, typically function R, the absolute value or the norm, okay? Typically, this is our example of dry friction that we will use in this talk, okay? So if you look at the history of the dry friction, it seems that the first studies of dry friction are due to Leonardo da Vinci, this polymath and also artist, famous Italian artist discovered indeed the friction force is proportional to law, and the friction opposes the motion, and it is independent of the contact area. This is a very important observation. So these fundamental results have been rediscovered later by Guillaume Amonton in the 17th, 18th century. And this French physicist was one of the pioneers in studying the problem of friction, that the resistance to motion where bodies are in contact, okay? So the Amonton's laws of friction says the following, that the force of friction is directly proportional to the applied law. This is what we call the first Amonton law. And the second one is that the force of friction is independent of the apparent area of contact. And we have to wait let's say the 18th century also, Charles Augustin de Coulomb, a French physicist, well known, to add a third law on friction. This is the kinetic friction is independent of the sliding velocity. So the laws here could be illustrated by this classical example of a brick resting in an inclined plane, and it is in equilibrium with motionless. Okay, the force of gravity is opposed by static friction, and the angle here that you have of tilt of the plane is increased when the brick will eventually start to move downwards as gravity overcomes the friction resistance. A simplification that we will use here of the Coulomb dry friction is given by the set-valued map. This is a beautiful maximal monotone operator in dimension 1, okay? And we will use it in this talk. By the way, this is what I call a simplification of the Coulomb law, since there are a lot of colleagues here online who knows very well the topic of dry friction. I want to emphasize that I will use just this simple friction law, okay? And there exists some non-monotone like this Strebeck friction law that can be used in for example, for the stick slip, to observe the stick slip phenomena. But I will not talk about non-monotone laws, since we are talking about optimization and convex analysis. The subdifferential here is in the sense of convex analysis. All right. Okay. So this is a simple model, simple mechanical example that I want just to give you. It's very famous, but I want to give you this model in order to observe something very interesting, is the convergence of the trajectory in finite time of the dynamic. We have here a mass. This is 1 DOF, 1 degree of freedom mass spring damper. We have a mass, we have a spring and the damper, and the damping C and K is the stiffness coefficient. And this mass is sliding on the floor, and the contact, we can model this contact with simple dry friction, as you see here, and it is the simplified Coulomb dry friction, if you like, monotone friction. If we write down the condition, the fundamental laws of Newton's, mass times the acceleration is equal to sum of forces, you will get this differential inclusion that you get here, okay? And of course here this subdifferential, since my function phi is only r, the absolute value, so its subdifferential is exactly minus, let's say, minus r plus r, okay? And you have the whole interval here. So if you look at the trajectory, the first thing to observe is the phase portrait, okay? This is the velocity versus the position versus the velocity. You will have here this set of equilibrium point. This is a set. It's not a single point. And this set is due to the set valued part of the friction, okay? And if you start the trajectory somewhere, you will be attracted in this to this set. And you see that the trajectory will converge in finite time. It means that there is some time, t, such that the trajectory converges to some point in this equilibrium. You see here the velocity will vanish also at some time. So the question is, could we have a mathematical result, say in general, saying that this under the dry friction, the dynamic will converge in finite time to an equilibrium, okay? So this is the question that I will answer just in a few seconds. And I have to mention that there exists some other works in other contexts, which is not of optimization. And I have to cite this work by Aman and Diaz in 2003 for the damped wave equation PDEs. Diaz, mu, this is Coulomb friction in the and oscillations for the damped oscillator here and the finite time convergence. Another paper by Baji, Kabou, and Diaz in 2007, when they studied the asymptotic behavior of the wave equation, and also they proved the finite time convergence, okay? of the trajectories. And another work in the context of Schrödinger equation by Carl and Gallo in 2011 for the finite time extension by nonlinear damping. Okay, and my talk will be completely different from all these previous works, and with Eddy we will focus on optimization. So the dry friction and its link with optimization. So let's get started. This is the outline of the talk. After this small introduction, I will introduce the continuous dynamic. It means inertial dynamic when we have both Hessian-driven damping and dry friction. After that, since we are interested in algorithms in optimization, I will introduce discrete inertial dynamic. Okay, it's the temporal discretization of this dynamic. And we gave some numerical experiments to test this kind of algorithms. Okay, at the end, I will give some conclusion and some perspective. Okay, so the context is the following. In my talk, phi is a convex continuous function. The minimum is sharp. With sharp minimum, typically in your mind, you can put that this function phi is R, the norm of this space. Okay. And we will suppose that 0 is in the interior, okay? What does it mean 0 in the interior of the subdifferential of phi at 0? So we have 4 equivalents. Each one has a very interesting interpretation. So this is evident 1 is equivalent to 2. It means that since we are in the topological interior, it means that there is a ball of size R inside this subdifferential. So we go to the duality, okay? So go to the support function, and you see that the support function to the subdifferential of phi is exactly the directional derivative, okay? Which will coincide here in this context with the, and the support function to the ball is exactly R times the norm. So we'll get that this function gonna be greater than or equal to R times the norm. This is a very interesting observation. It means that I have all my functions that I will consider. We have R. R is the coefficient of dry friction. And I consider all functions which are convex and beyond, okay, with sharp minimum here, of course, and beyond this function, the R times the norm. And we have this fourth equivalent that we have here, which is very interesting. It means that if you are inside this ball, okay, because you know that when you write down this function, the f is in the subdifferential of phi at, let's say, x, this is equivalent to say that x is in the subdifferential of phi star at f, okay, when phi star is exactly the Fenchel conjugate. The mechanical interpretation is that f is 4 are forces, and the x is the displacement, could be also the velocity if you are working in the dynamic case. F are the forces. So we have forces linked to the displacement or the velocities, okay, via this subdifferential, and you can invert. We have here the position linked to the forces. It means that, well, if these forces are less than some threshold R, then the velocity will vanish. This is the interpretation of the inclusion number 4. Okay, so for my talk, when I'm talking about, we say that the friction potential phi satisfies the property df with the parameter R if this condition is satisfied. Okay, so now the dynamic is the following, as you see here. And we have this general theorem that says that for any given, let's say that the coefficient here, gamma, could be constant or even variable with time t, okay? What says exactly this theorem that for any initial condition, the dynamic, the Cauchy problem has a unique solution. This is very classic, okay? But we will have that when the trajectory x of t, since you are working here in time t, which is interval 0 plus infinity, we have that the trajectory will converge to some point x infinity. And this point will satisfy, since you see here that the acceleration will vanish. This term, this is the viscous friction will vanish, okay? So you will have this inclusion, number 2, which means that the minus gradient of f at x infinity is in the subdifferential of phi at 0. This is the stationary equation, okay, or the equilibrium. So we have to observe what happens if phi is 0. If we don't have any dry friction, so we will get only a stationary point. This is the link with optimization, okay? We got a stationary point. But here we don't have a stationary point. It depends on the size of this subdifferential that we have here. If this subdifferential of phi at 0 is small, then this is kind of epsilon stationary point, okay? So this is the link between the optimization. You have to pay a price if you want to introduce the dry friction. You will not get exactly a critical point, but you will get something which is linked to this inclusion. It depends on the size of the dry friction. So the most interesting property is property number 3, okay, that we have here. What says exactly this property? If this minus the gradient of f at x infinity is not in the boundary of this set, okay, which is the subdifferential of phi at 0, then there are convergence of the trajectory in finite time, okay? This is the most interesting property, okay? I can illustrate this in this figure. We have here, this is the subdifferential of phi at 0. This is a nice convex and compact set. We are in dimension 2, okay? You have a point here that I call minus the gradient of f at x infinity. You are in the interior. It means that there is a ball here, a small ball with radius r. So the finite time will depend how far, okay, how far is this point from the boundary. This is why I have the finite time t1 will be, let's say, less than some constant. And this constant will depend, of course, the velocity of some point t0, but I'm not have time to explain what is t0 here. But what is interesting is the denominator. What we have in the denominator is the distance from this point that we have here to the boundary of the subdifferential. If this point is close to the boundary, it means that this distance is goes to 0. Then we will have convergence. It could be convergence in infinite because this will go to infinity, okay? If you are close enough to the boundary, okay? So we can illustrate this via a simple example, dynamic in dimension 2, that we have, dimension 1, sorry, with the absolute value, okay? And you will see that in this case, we have a solution which converge in infinite time, okay? Because the condition of the interior condition is not satisfied in this case. This is a simple dynamic. You have -1, okay? And you have +1. If you start here, you will converge like this. If you start here, the dynamic will go there. This is t. This is x of t, okay? However, the convergence does not hold in finite time if the interior condition is not satisfied, okay? Let's go now and try to study this dynamic from the discrete perspective. Okay, so now we have this dynamic, which is continuous dynamic in time, t. We will discretize the velocity. This is the discretization of the velocity. We take some h, which is the step size. We discretize sorry, this is the acceleration. Oh, sorry, I'm sorry. This is the discretization of the acceleration. This is the discretization of the velocity. You see here, this is the discretization of the velocity. And we can put it explicit via the smooth potential, and it's going to be explicit, implicit via the non-differential potential, which is phi here. Okay, so we are solving for xk plus 1. So in order to get xk plus 1, we got this equation when we, the prox of the function phi, I have to recall some background from convex analysis. The prox of lambda phi is exactly the identity plus lambda, the subdifferential of phi inverse. Okay, this is a well-known proximal operator. Okay, and you solve for xk plus 1 to get here, given two initial points. You will compute this point, which is a very simple point to compute. Let's say this is my zk. Okay, and you can put xk plus 1 is equal to xk plus h prox of this function here. All right. Okay. So what happened? The question is, do we have convergence of this sequence xk to some point? And this point, is it an equilibrium point of the dynamic? Okay, like the continuous case. And the question is, do we have this finite time convergence? It means finite convergence in finite steps for the discrete. Usually we lose some properties when we pass from continuous to dynamic, continuous dynamics to discrete dynamics, because some properties could be lost. But in this case, we will show that the same pattern will be valid. It means that the sequence xk will converge in finite time, finite steps, sorry. So the assumptions of the problem are the function f is of class C1. We suppose that its gradient is Lipschitz with constant L, with modulus L. We don't suppose here any convexity on the function, on the potential to minimize, okay? As you see here. We suppose, of course, that the infimum exists, is greater than minus infinity. And we suppose that our function h here satisfies the dry friction assumptions. Okay. So now look at this theorem, which shows the finite length property, which is a kind of assumption more strong than the usual convergence. So if you tune these parameters, we have this is the h, gamma, okay, and L. We have three parameters here. H is the step size, gamma is the viscous damping friction, and L is the constant of Lipschitz of the gradient of the function f to minimize. Okay, if you tune those parameters, it means that this condition is satisfied. Then first condition that we have here is that the finite length property, it means that the series norm xk plus 1 minus xk is finite. This is very interesting property because it implies automatically that the sequence xk will converge with respect to the strong topology in H. Okay, so this is a very interesting property, and we can show more that this here in the paper, but with ED, that this series is dominated by 1 over R E1. When E1 is only the Lyapunov energy that you have here. Okay. And also we have this condition about the acceleration, but it doesn't, I will not have time to talk about all this stuff. Okay. The second property is that the limit, since now we have this finite length property, which implies that the sequence will converge, then the limit point will satisfy exactly our assumption, stationary point. It means that it's a stationary point. Let me remind you that when phi is 0, this is only a critical point. And we have to take the subdifferential of phi at 0 very small in order to get on something which is almost a minimum. Okay. So now we switch to the interior. What happened if we have this condition, which is the same as the continuous dynamic? Do we have finite convergence of the sequence? It means that the sequence will stop at certain iterations. Okay.
I'm sorry, I have a question. Can I interrupt?
Yes.
Sorry, a quick question. In this discrete dynamics, is the next iteration uniquely defined? Is it a single valued function, xk plus 1 of the previous?
Of course. This is
well
defined. This is, you have here equality because of the prox. The prox of a function is the identity plus lambda the subdifferential inverse is a single valued with nice properties.
Okay. Yeah,
which is Lipschitz, continuous, and single value. It is a single value. This is why I have here equality. You see it here? Maybe I have to change the color. We have here equality. Okay.
I see. Thank you.
This is due to the prox. This is the property of the proximal mapping. Okay, thank you for the question.
Yeah.
All right. Now the question is, do we have the same condition as the continuous case when with the interior condition? Okay. So now this theorem that we proved with Eddy, this first paper that is available here. Okay. If the interior condition is satisfied, then there is a geometric convergence. You have here a geometric convergence which depends on this Q. But anyway, if we suppose that the gradient is less strictly than some R, it means that you are in the interior, then the sequence will finitely converge. It means that the dry friction will act like the control will stop the system after some iterations. Okay. So there is an open question that we cannot estimate, unfortunately, the number of iterations at which the dynamic will or the sequence will stop. Okay, you see here that the discrete temporal dynamic and the continuous dynamic will have the same pattern. It means that the trajectory in the continuous converge in finite time, and here the sequence will converge also in finite time. Okay. So let's move now to the Hessian damping. I did not talk about the introduction now to the Hessian. This is just a small introduction to the dry friction in the context of optimization. Okay, so now for the Hessian, if we have the same dynamic, but without the dry friction for the moment, I have here a new term which involves the Hessian matrix of F. This means that you have to suppose some regularity, at least C2 of the function F to minimize, okay? And why this kind of dynamic is important. So we can start the story by some historical aspect, and the work by Polyak for the heavy ball with dry friction. The heavy ball with dry friction is a very simple phenomena. Observed, you have a ball which will explore all the minima of the function, okay? And also the work by Alvarez in 2002 for when we put here instead of x dot an operator, okay? But there is an interesting work in 2002, okay, by Alvarez, Atouche, Bolt, Rodin, okay? When they use this dynamic, we have here two coefficients. The first one is gamma is attached to the viscous damping. And the second one is beta is attached to the Hessian, this is a geometrical damping, okay? And another interesting work by Atouche, Pepouquet, Rodin in 2016, and another one by Shidou, Jordan, Su, okay, in 2018. Another one here in 2019 by Atouche, Beni, Fadili, Atouche, Bot, Chesnek, Laszlo in 2019 also. The only difference here is that we consider asymptotic vanishing, as you see here, it's alpha over t, and you see when t goes to infinity, this is what we call the asymptotic vanishing damping. Okay, it's not easy to to extend the result from a constant damping to the asymptotic vanishing damping. But anyway, it's linked to the acceleration, Nesterov, etc. And what I want to emphasize here is why the Hessian-driven damping is interesting. It attenuates the oscillations effect, because it is well known that if you don't have this term, this is the heavy ball, we will have oscillation, as we see from this simple example taken from a paper by Atoush Bani Fadil Riai. And you see that we have oscillations here in this graph, okay? And if you put the Hessian, this is a geometrical damping, okay? Then this oscillation will be attenuated and even will disappear, okay? And the work with AD that we did recently is to combine, let's say, 3 dampings. Now, what kind of damping we have here? The first one is classical. This is the viscous damping. This is the geometrical damping linked to the Hessian, okay, driven damping. And we add the dry friction damping. And we want to see if this kind of properties that I gave you before, both for the continuous case and the discrete case, will be valid. Okay. After discretization of this dynamic, in the same way as before, this is the velocity. This is the discrete acceleration. This is the discrete velocity. This is the discrete. But one observation that even we have a second order term in the dynamic, we can see that this is only the derivative of the gradient of f at x of t. This term is exactly this. So in the discretization, you will have only equations of first order. Okay, we will have only a first order in terms of the gradient of f. It means that the Hessian is not involved in the discrete, as you see here. When you discretize and you solve, you will get to equation xk plus 1 equal xk plus h, the prox of this function, the same, evaluated at zk. And you see in zk, this is the point, this is the gradient, and this is another gradient, okay? This is, even we have a second, this is the most interesting property, even we have a second order dynamic, in time, of course, but second order also in terms of the Hessian will not appear. It means that we will need only to evaluate the function, the gradient of the function f, not the Hessian, okay? So this first theorem says that if you tune very well your parameters, gamma is the viscous damping, L the gradient, the Lipschitz gradient, and H is the step size, beta is the constant linked to the geometrical damping, which is driven by the Hessian. Then we'll have also finite length property. It means convergence into the strong topology. And of course, the limit will satisfy the equilibrium equation, the stationary equation that we have here, okay? So this, in the same way, if the interior condition is satisfied, then we will have this geometrical convergence, okay? And if you are in the interior, it means that the gradient is less than some parameter r, then the sequence is finitely convergent. It means that the same properties are still valid for this algorithm, okay? So now I want to talk, because I have 10 minutes before finishing my talk, the link between this kind of inertial proximal algorithm and the Nesterov acceleration. As you know, Nesterov acceleration is well known and well developed, and many communities, particularly community for machine learning, are using this kind of methods to simulate many concrete problems linked with the artificial intelligence, etc. And as you see here, we suppose that we want to minimize a function f, which is, let's say, differentiable, etc., with I will suppose here that we have asymptotic vanishing damping, alpha over t, okay? And we have only a gradient here to suppose this is only a simple dynamic, okay? We go to this temporal discretization, we got this equation, and we have here some yk. And this yk, there are many ways to choose it, and the way chosen by Nesterov, okay, is given by this formula, okay, linked, of course, to this alpha. Alpha is the coefficient of asymptotic vanishing damping. This is AV.
A question.
Yeah.
So this Nesterov acceleration only appears in discretization, not in the initial equation.
You are talking about the acceleration for the part when I discretize this equation. I got this. I go from this equation. Okay, this is a dynamic. I discretize. I put here some yk, and this yk, if you put yk is equal to xk, you got the classical heavy ball with friction, all right? But if you put this yk in this way here, this is what we call the Nesterov. But if we put yk is exactly xk plus 1, okay, it means
I see.
Then we got the inertial proximal algorithm that we have here.
Okay, because acceleration in your talk means acceleration of the computational algorithm, not
exactly,
not
right.
physical.
You're absolutely right. The acceleration here is linked not to the dynamic. I'm sorry about the confusion. It is linked to we have an algorithm, and we want fast algorithm to go to the minimum as fast as possible. This is an optimization community. We call this acceleration of algorithms, okay, for the minimization of function. It is not the derivative of the velocity, okay? I'm sorry for this confusion, right? But anyway, we have here just a simple interpretation between Nesterov acceleration, okay, of algorithms. If you start from this point here, xk minus 1 xk, and you go, your yk is given by this formula, okay? You are orthogonal to this level set, and you are looking for xk plus 1, which given by this formula. Where the initial proximal algorithm, you have from yk to go until being orthogonal to this level set. This is just a geometrical interpretation between to have an idea what we mean by Nesterov acceleration and inertial proximal algorithm. Okay, so now I want to apply this kind of problem to minimize the sum of two functions. It means that in terms of mechanics, we have two potential. One is differentiable and the other one is not differentiable. Okay. My first function is convex C1 with gradient Lipschitz, and the second one is only convex lower semi-continuous, proper, could be extended real valued function, okay? So you have this yk, okay, and we have this xk plus, so this is the inertial proximal algorithm with alpha. What is interesting is that this alpha that is involved in the AVD, asymptotic vanishing damping, it has a mysterious some mysterious interpretation, and it's a little bit amazing to know that the choice of this parameter is very, very, very important in computation. Okay, and still many open questions are to be answered. For example, when this alpha is 3, we got Nesterov acceleration, or back to Boole, which we call FISTA, fast iteration threshold algorithm. Okay, it was introduced in 2009, and when alpha is greater than 3, the choice of 3, we don't have any interpretation. Maybe it is linked to Lyapunov function, but we don't have any interpretation for the moment. Why 3? When alpha is greater than 3, this is what we call the over damping. This we can prove. It was done by Chambol Dossal in 2015 and Atouche-Pepouquet in 2016, that the trajectory, the sequence xk will converge weakly to some point which is a minimum of the sum of the two functions. Okay, And the under damping was also studied recently by Apidopoulos, Ojol, and Atoush Beneria in 2018. Okay, so now we will combine, okay, all this stuff with the Nesterov acceleration, okay, of the algorithm. Okay, and we have here this yk that you see. Yk is given by this. You compute this zk. And we have xk plus 1, which is exactly xk plus h the prox at zk. Okay, so now we got the same results. You have to tune your parameters. Okay, and we will have first that the sequence will satisfy the finite length convergence property, which means that we have convergence in the strong topology. The limit point will satisfy the equilibrium equation, the stationary point, and we can observe also the question if we have finite convergence or not. Okay, this is in this slide I just to mention that by taking another discretization of the velocity rather than taking this discretization than taking this discretization here, we take this one. Okay, we can have another variant of the algorithm with which is completely different from the first one, but have the same properties. Okay, so now you can ask me what happens if my first potential f is not smooth, okay, but convex, for example. It is possible, okay, the first potential that I mentioned from the beginning was of class C1, okay, and with the gradient L Lipschitz. This is my assumptions. It is possible if your function f is, let's say, in gamma naught of h. We use the notation by Jean-Jacques Moreau. This is the set of all convex lower semi-consistent power function. It is possible to replace when f is non-smooth but convex, to replace it by the Moreau envelope, okay, f lambda, and the Moreau envelope is given by this formula, which is the minimum only of the f plus the quadratic term that you have here. Okay, over there is the scaling lambda here is given. So we got a non-smooth system, but it is also well defined. Comparing the question by Esther, it is also well defined, but instead of the function will not enter the algorithm via the gradient as before, it will enter you see here, before I got here the gradient of f at xk and the gradient of f here, the gradient of f here. And now my function is not differentiable, so I'll replace it by the prox of lambda. This is prox. Before I got something which is backward forward, like prox and the gradient, the prox of the phi. Before I got the prox of the function phi and the gradient of the function f. But now, since my function is not convex, is not smooth, sorry, we can do the same analysis to have this. Okay, and now I want to show you, just because I have 2 minutes, to show you the application of this in the well-known splitting algorithm for what we call the Lasso-type problems. It means you minimize a quadratic function plus a non-smooth function. Okay, all right. What kind? You can ask me how to compute this prox of this function here, of this function phi. Since I told you that my function phi is in general more or less with sharp minimum, it means that the r times the norm. So we have an exact closed formula that we have here. If the function phi is r times the norm, then the prox is computed, which is exactly this this formula given here. Okay, if you are less than this, it is 0, and you have this anyway. You can have the formula exact. Okay, and if your function that you want to minimize, which is not smooth, also of norm 1, okay, you can compute its prox exactly component wise, but you can compute, we have a closed formula for that. So now I will compare 4 algorithms that IPAD, initial proximal algorithms with dry friction and Hessian damping. Okay, we have 2 variants. Okay, the N, it means then with Nesterov acceleration, and var, it means this is the variant. Okay, and to compare these algorithms, this is a very interesting question in mathematics and numerical analysis in general, how to compare algorithms. We will not compare algorithm in one example and say that my algorithm is better than this one. In optimization community, they use what we call the Dolan-Moret benchmarking. Okay, this is the performance profile developed by Dolan and Moret, and it appeared in mathematical program in 2002. And we will use this Dolan-Moret. It means you have to generate a lot of problems and to see which one is the best. Okay, I will go directly to the numerical examples, and you see from this performance profile that the IPAD N Nesterov with variant is the best. You see here it solves all the problems and very fastly. The worst one is the red one because the curve is less. It solves in this interval only some problems. Okay, and for this problem also, for this kind of problem, we have the Nesterov with variant is the best. Okay, and this one they have we put beta, it means with geometrical damping and without beta. Let me remind you that beta is linked to the Hessian, okay, of the function. If you put beta, then the acceleration you see here, because I told you that this geometrical damping will attenuate all oscillations and also could be
just scroll down by 1 line. Yeah, like this. Yeah.
All right, sorry. And this is without and with geometrical damping. Okay, so now it's time to conclude. So the algorithm that I have nothing to hide here. The algorithm that we propose work with general smooth function without convexity. Okay, assumption could be extended to non-smooth function but convex. Okay, via the Moreau envelope. It is also robust. We did not have time to, it is in the paper because we can tolerate 2 perturbation and errors. And this naturally suggests developing corresponding stochastic version, okay, combining also dry friction. And the analysis was done with the fixed damping coefficient gamma, okay. It will be interesting to consider or an asymptotic vanishing damping, but the analysis, the Lyapunov functions and the mathematical analysis could be harder. This allow dry friction to be considered also in the Nesterov fast gradient method. Okay, so thank you very much for your patience, and I'm sorry I have 1 or 2 minutes more. This is the paper that you can find on the net, and also some other references, okay, that are interesting. This one we wrote with Alexandre Cabot, and also this one when I use this paper for the oscillation of the to attenuate the oscillation of the geometrical damping driven by the Hessian. Thank you very much for your attention.